So used for, by timekeeping, I literally mean like a stopwatch, start, stop. Right? That's what it does. So like a stopwatch. Okay, they have applications in many things. I'll list a few. Bounce free switches. Cascaded timers. Frequency. Dividers. Oscillators. LED flashes and so on. Okay, so what's inside a 555 timer? As you can see here in the figure, there are two op-amps. Okay, there is one RS flip-flop, which is here, and then there is one BJT, or a bipolar junction transistor, right here. Okay, you've probably seen the pinout for a 555 IC. You use it in the lab, so you probably have seen it. Yeah, I'll not go into detail of that, but I'll show you, I'll sort of explain to you how it works. It's actually something which combines knowledge of op-amps, bipolar junction transistor, and RS flip-flop, all things you need in order to figure out how it works. So there are two configurations we'll discuss. Well, I'll only explain one, and then the other one you can figure out yourself. So two modes of operation. Monostable vibrator, and then a stable vibrator. Okay, so before I show you, so what you see here is the chip, but then it's connected to a resistor and a capacitor. Okay, the same thing you did in the lab. Now we also have a RS flip-flop. So let me draw the truth table of RS flip-flop because we will need it. Okay, so R, S, and then Q bar. Okay, so we have 0, 0. We'll leave this unchanged. We have 1, 0. So R is 1, means it's reset. So 1, 0. And then we have 0, 1, which is set, 0, 1. That's all. The 1, 1 is not allowed. Okay, so we got that. Okay, now the working of the 555 timer under this circumstances where it's connected to RA and C. Okay, so it's basically going to be 4 steps. Okay, then you need to follow it step by step. So first, one thing you need to note is that this RS flip-flop actually has a reset pin, just like a JK flip-flop. So what you need to do is you need to take the reset is pressed. Okay. What that will do is it will set R equals S equals 0, and I'll just highlight that because we'll summarize later on. So that will make R equals S equals 0. Okay. A consequence of setting RS equals 0 is that Q will be 0. Okay, so this is something which does not exist here because traditionally RS flip flop doesn't have the reset, but this one does. And pressing the reset will actually give you the following output. Now, setting Q bar to 1, what that does is basically turns on the junction transistor, and it leads to the capacitor draining of any voltage which exists on it. So from a previous operation, maybe the capacitor had some charge, and that will be drained by setting it. So this turns the BJT on and drains the capacitor of charge. So it's discharge at this point. Yes, that's step number 1. Okay, now what happens is once it's reset, now we come to this this figure here. Okay, so now this is a trigger pulse. Remember that the chip had a trigger. So this trigger is like a clock. It goes off and on, 0, 1, and 0. So let's say that it goes down. So here is VCC. Okay, so normally VCC is constant, but because the trigger, you can ensure that it leads to sort of like a clock pulse. So when this reaches 1/3 VCC, again, for a good reason, I wrote 1/3 because you can see here there's 1/3 VCC and 2/3 VCC. So that 1/3 VCC and 2/3 VCC is because if you do voltage divider across these 3 resistors, you see that the voltage across this would be 2/3 of the total resistance, and this would be 1/3, right? Because this is VCC, this is ground. So you can use the voltage resistor to figure that out. Okay, so the voltage here is 2/3 VCC, here it's 1/3 VCC because of voltage divider theorem. Okay, now what happens is, let's say that you pass this VCC, it goes to 1/3, which it's trailing. Once it goes to 1/3 VCC, note the trigger is connected here. Okay. So the role of a comparator is to compare the inputs, and it will go high when this plus is greater than negative. It will change state, go from 0 to 1 or 1 to 0. So what happens here is that when this trigger goes below 1/3 VCC, you'll see that this goes 1. The output is 1. That is, this logical condition is true. So it becomes less than 1/3. This is so good. This maps here. This goes 1. Okay, what that does that mean? It means that S equals 1, right? But R remains 0. And from the truth table, we see that S equals 1 means Q equals 0, Q equals, we write this way so it's less confusing. R equals 0, S equals 1, Q will be equal to 0, Q bar will be equal to 1. So what has happened here is Q equals 0. So the output is 0. Something is wrong. If S equals 1, let's switch it. Maybe I got my logic of the comparator wrong. No, I think my truth table is wrong. Yeah, my truth table is wrong. My bad. The truth table was wrong. This is S, this is R. Okay, so if S equals 1, R equals 0. Okay, so this is incorrect. Q equals 1, Q bar equals 0. Okay, so what we care about is Q. Output is 1. So we can see here from the circuit diagram, from the, sorry, this timing diagram, that once it reaches 1/3 VCC, this goes 1. So this is number 2. I use the red color. Okay, so this is 1. This S, sorry, this 1/3 VCC is triggering let me write it down. Thus, output equals Q equals 1. Okay, that's step number 2. Now, next what happens is next we have this clock remains 0, so we don't have to worry, it just stays, maintains the state, nothing special is happening in the SR, it's just going to remember its state. Then, however, here we see that there is a rising edge. Now what happens is we need to look at again 1/3 VCC. So now it's going to go up. When it goes up, this reaches 1/3 VCC. So this was 0, now it goes to 1/3 VCC. And that actually causes the other comparator to trigger. That's right, so it goes to 2/3 VCC. So when it goes to 2/3 VCC, that triggers the other comparator. And now this one goes to 1. Sorry, this one goes to, my bad, just ignore that. That's not true. So you don't have to look at 2/3, but 1/3 VCC. When it reaches 1/3 VCC, my bad, this one is going to now flip, because it was 1 when this voltage went below 1/3 VCC. When it reaches above 1/3 VCC right over here, this one is going to flip from 1 to 0. So when it flips from 1 to 0, you see that, let me write that down here, when R equals, so here, when B is greater than 1/3 VCC, S equals 0, so the S has flipped. R will not change. Unchanged. And when S equals 0, R equals 0, Q0 bar is unchanged. So Q equals Q0, but Q0 is the same as what it was before 1. And Q bar is what it was previously, which is 0. So nothing is changed, no change in the output. And that can be seen in this circuit. If you look here, when this took place, there was no change. Okay, now what happens is the final step, and we're almost done. Now, remember there's a capacitor, and the capacitor is going to start charging up. Here the capacitor keeps charging because there's a voltage applied across it. And so the reason why it's charging in that exponential fashion is because if you remember, when we looked at RC filters, it basically doesn't charge immediately, but it will show this characteristic curve, which is an exponential, which comes because of the resistor and capacitor in series. So it's going to, this R and C is going to make it charge slowly. When it reaches 2/3 VCC, so the capacitor now is 2/3 VCC, but this 2/3 VCC is also across this comparator. So when it reaches 2/3 VCC, the threshold comparator will flip because that logic has been, so when capacitor charges to 2/3 VCC, R will become 1, okay, because it's a different color. Let me just show this on here. Okay. When R will become 1, but S will be unchanged from the previous one. But when R equals 1 and S equals 0, Q becomes 0, right? So Q equals 0, Q bar equals 1, which means that output equals 0. The output equals Q0, Q equals 0. Okay, so you see that right here, the output goes from 1 to 0. Okay, so that's the explanation. It's kind of, sometimes very difficult to wrap your head around it. But the key thing here to remember is that okay, so number one is that, remember what I said, just to summarize, the output is high. Okay, the output is high due to this step. And the output is 0 for this step. Right? That's what we care about. Why is that? Why does that happen? This one happens because of the trigger. You can see trigger comparator. So the trigger comparator reaches 1/3 VCC, and that triggers the output high. But if you want to understand why does the output get low, you see it's here, and that happens because of two things. One is the capacitor charges to 2/3 VCC, which is shown here, and the second thing is that the threshold comparator flips. So the output is low because one, capacitor charges, and two, threshold comparator flips. Okay, so that's how the 555 timer works. And remember that the capacitor charging is not just the capacitor; it's just this RC. So you can tune the timer by changing this time constant, which is a function of R and C. And that's why when you change the resistor in the 555 timer, you saw whatever you saw, right? You were able to change the frequency of the timing. Okay, the other one I'm not going to talk, but this is another configuration called A-stable multi-vibrator. It basically has two time constants, T1 and T2. Okay, so T1 is R1 plus R2 times C. You can see that the R1 connected here, R2 connected here into the capacitor. So it uses two resistors and one capacitor. This is the timing for T1. The timing for T2 is R2C. Okay, so this one is beneficial because if you want to have a peak for a time which is different from the time the output is low, then you want to use a stable multi-vibrator, because it will let you tune these resistances so that you get different times. Okay, so that's the configuration we've not seen in the lab, but it can actually be explained with the same logic as the one I used. You need to reason with the capacitor. You'll see that there is a charging part, there's a discharging part. Both those parts are important. The charging part, you will have the R1 and C. So the explanation for that is going to be very similar to what I gave. So here we have C, R1 plus R2 in series, and that part is probably very similar to what I described. But then the discharge part is 1 due to R2 and C, as you can see from the equations. So you need to reason out how this is going to lead to the behavior resistance.